But I just want to rehash to make sure that we all fully understand what's going on. The first thing I guess I should probably say is if we deal in the coordinate plane with, let's say, that angle right there, the things that I learn about that angle that is 30 degrees would be exactly the same thing that I learn about that angle that has a 30-degree angle measurement, right? Different location, correct? But it's the same thing that I would learn about that angle. It's the same thing that I would learn maybe about a 30-degree angle down here in the fourth quadrant, okay? So because of that fact, and those of you that are in physics might know this already, okay? Because of your work with vectors. Because of that fact that no matter where this angle exists, it's 30 degrees. And what I learn about it here is the same that I would learn about it there. Hopefully then it makes sense for us to want to put it right there. Does that kind of make sense? Okay. If you guys are in physics, you've dealt with vectors, and you've thought maybe, or you've dealt with maybe, let's say, that vector right there, right? Oh, just want to deal with one of them. That vector there. But you learned that that is the same vector right there, right? And you have learned that it's the same vector there, okay? And we talk about vectors in physics. We talk about their ordered pairs, right? And we do some work with their ordered pairs of their, call them the tip and their tail, right? Okay. Well, if that vector and that vector are the same, and that vector and that vector are the same, then all those vectors along with this one are the same, right? And what's convenient about that one? That vector has an ordered pair of 0, 0, right? And addition and subtraction with 0, 0 is so much easier than addition and subtraction with numbers that are non-zero. So the same concept, same principle kind of applies. If you understood that from physics, the same principle applies when we're talking about angles. If we can position them at 0, 0, it makes a lot of our work a lot simpler, okay? But what we're seeing here is that if I take, let's see here. If I take this vector, which is just the side of an angle, so I take this ray, and I trace it out. Come on. Detach. Sorry. There you go. And I start tracing that thing, okay? It is now traced out a 30-degree angle, right? Well, if I start at that 30-degree angle and I start going all the way around again, okay? Everything that is blue now, all that tracing point, is how many degrees? How many? Careful. 390, right? Okay. How do I get that 390? Yeah, it was the 360 is from where my cursor is now, all the way around back to there, right? Okay. But then I had this additional 30 tagged onto it. Okay. So that angle that you just saw, let me do it again. Sorry, hold on a second. All right. So right now I got a 30-degree angle, right? So the angle that's being traced out by that orange ray to there is what we refer to as a coterminal angle. Does it stop? Does it terminate at the exact same spot that the 30-degree angle stopped at? Is it orange ray on top of the black ray? So they stop at the same spot? Yeah, they stop at the exact same location in the first quadrant, right? So those are referred to as coterminal angles. Okay? The way I find those is I simply add 360 degrees to one of them. Okay? So let's say I want another one. Right now, if that blue stuff is traced out 390 degrees, right? Well, trace out another 360. Does it get me back to the same spot? So 390 plus 360, what's it give me, 750? So 750 degrees is a coterminal angle with 30 degrees, which is a coterminal angle with 390 degrees. Is that doable? Does that make sense? Okay. I think on Friday, or not Friday, Thursday, maybe I did this. I think I pasted this in here. So we're going to do it again. So you see that when I paste this over top of C, so this is image A pasted on top of C, do the two blue rays land on top of one another. And when that happens, the angles that form those two blue rays are referred to as coterminal angle. Co meaning together, terminal means end, right? So they end together, they stop at the same spot. Okay? We like to talk about coterminal angles and be able to deal with them. Okay? Just through those are standard position. Standard position is when there's the idea of placing the vertex at 0, 0, and then one of your rays, we call it the initial ray, to be the positive x-axis. So there's an array of an angle there, there's an array of our angle there, and there. Okay? Now, the reason I show this picture is because a lot of your questions in your homework are not going to be they're not going to be videos. They're not going to be dynamic. You're going to see them trace out that direction. So you'll put this little arrow right there. That tells you the direction that thing should be moving. Or they put the arrow here, and now they say that this ray, okay, starts moving that direction clockwise, and then the angle that we're interested in, obviously that red angle is being traced out with that arc. Does that make sense? When they show the circle go, or the arc go around all the way around multiple times, so there's one complete revolution, and then plus a little bit more. So we know that angle is bigger than 360, but less than 720, because it's only showing one complete revolution of 360. But if I look at this one here, we go around one time, so that's 360 to there. And then we go around 180 degrees, so what's that, 540? And then a little bit further. Okay, so I know that this angle here is a little bit bigger than 540. Does that make sense? All right. So it says down here, can you find coterminal angles if you start off with an angle that's 30 degrees? Okay. So the nice thing is that it says you were in 30 degrees. We kind of already did this one, but we'll do it again. So there's my initial ray. There's my terminal ray. Say that's 30 degrees. Okay, and that's the theta. You guys know what that's theta? That's what we call that. Okay. Okay, Greek letter theta. It's just the variable that we use, kind of like in algebra, the kind of standard variable is x, right? Well, in trig, the standard variable is theta. And a lot of times in regards to angle measurements, and when angles are variables, we use the Greek letters. Okay, so theta is kind of the standard, traditional one we use. But like in algebra, we can use x, y, z, any letter we want to, right? So we can use theta. We'll see gamma here. We'll see, I think later on we see omega in this section. So we'll see other Greek letters, but they just stand in for variables that represent usually angles. Okay, so that's what we're saying here, that this theta right there is 30 degrees. Well, if that's 30 degrees, how can I find an angle that's coterminal with it? What do I need to add to that? 360. So go 30 plus 360 will give me 390, right? How do I find another one that would be coterminal with that? Add 360 again, right? And so give me 750. How do I find another one? Add 360. I keep doing that, right? Okay. Well, what if I wanted to go the other direction? What if I'm at 30 degrees right now, and I want to go that direction? Subtract 360. So subtract 360 from here, and you get negative 330. So a negative 330 degree angle is exactly the same as a 30 degree angle. Does that make sense? Or what we learn about is exactly the same. So if they ever gave me in a problem, they say, we'll see this here soon. They say, find the cosine of negative 330. I'm not going to do that. I'm going to find cosine of 30. Does that make sense? Okay. It just makes things a little bit easier if we can deal with those coterminal angles. Usually puts them in smaller amounts for us. Okay. If I want to find another one, I would subtract another 360, right? And I can keep doing it. Keep subtracting iterations of 360 or adding iterations of 360. So what that does for us is it provides us a formula. Okay. We start with our theta, and we're going to add to it 360 times k. Basically, that says all you're going to do is you're going to add multiples of 360, right? Okay. But we're going to say theta obviously is your initial angle. But k, this is usually the way you see it, k, and they put this little e symbol. Anybody know what that means? Talked about it initially in college algebra a little bit. Is an element. K is an element, or K belongs to. Do you remember what these numbers were? What Z is? Z is your set of integers. Okay? So say K is allowed to be 0. Okay, so if K was 0, I'm just getting that initial 30 degrees, right? Okay. If K is 1, I have 30 plus 360. If K is 2, I have 30 plus that 360 plus that 360, right? So I have 30 plus 720, right? So I'm just adding multiples or revolutions around that circle when K is a positive number. When K is negative 1, that's subtracting 360, right? When K is negative 2, it's subtracting 720. So that's a formula for finding coterminal angles. I think in your homework, you're going to probably find in the ad, they'll give you an angle and say, okay, find the first 2 positive coterminal angles, and then find the first 2 negative coterminal angles. And all you got to do is add 360 twice and subtract 360 twice. Is that doable? Okay. Down here at the bottom, it says find angles that are coterminal with the angle theta equals pi over 3. All right, so if we're looking at pi over 3, and you will learn this, it'll be kind of second nature to you here eventually. But pi over 3 might look something like that. That's my theta. So we're in radian. Remember, whenever you see, when it's not written, the unit is understood to be radians. Okay, they'll never write like pi over 3 degrees. It doesn't make sense to write that way. So when the unit of an angle is not written down, they're implying radians. So when I want to talk about radians, what was the measurement that was equivalent to 360 degrees in radians? 360 degrees was how many radians? 2 pi. So if I start with pi over 3, and I want to take this ray right here and basically rotate it so it gets back to itself, if it was in degrees, that would be a rotation of 360 degrees, right? But in radians, it's a rotation of 2 pi. So you want to add 2 pi to that thing. Okay. Now, what do I need if I'm going to add 2 fractions? Common denominator. So that common denominator is going to be a 3, right? And that numerator is going to be a 6 pi. I think a byproduct should be a plus sign. This should be a plus sign. A byproduct of this course is that you are going to get much better at dealing with fractions. Okay? Learning your rules and your properties and all your algebra that is applied and required for fractions. Okay? So when I add those together, I get 7 pi over 3, right? How do I get another coterminal angle with it? What can I add to 7 pi over 3 again? 6 pi over 3. So then 13 pi over 3. That angle, that angle, that angle. They're all coterminal, right? Okay. And I can keep doing that. So, our formula here, it's the exact same thing we had up here. We had theta plus 360k, right? Well, down here, it's going to be theta plus 2 pi k. K is still an integer. So that tells us that, because a lot of people think, well, I need a formula that will do addition for me, but I also need a formula to do subtraction for me. Well, if I let k be an integer, that incorporates multiplying this by a negative at some point, right? And that turns it into the subtraction formula. Okay. So if k was -1, you could have pi over 3 minus 6 pi over 3, and that gives you negative 5 pi over 3 as one of your coterminal lengths. Okay. So dealing with coterminal angles is going to be important. This next example is why it's important. Okay. We might go through some work at some point in this course, and we might get a result that says 1290 degrees. Or maybe we have to eventually, maybe, like I asked you earlier, what's the cosine of 1290? Or what's the sine of 1290? Or the tangent of 1290? Those are questions that we're going to be interested in. Well, that's really hard to do. But if I can reduce that thing down to a coterminal angle that's between 0 and 360, it's going to be a lot easier. Okay? So all we do is take our 1290, and I want to start subtracting iterations of 360, or multiples of 360, until I get down to a amount that is between 0 and 360. So if I subtract 360, obviously that one's not going to be in there. Subtract 360 again. So 1290 minus 720 is still bigger than 360. So then I subtract 360 one more time. And I believe if I do that, should get 210 degrees, right? 210 degrees is the only coterminal angle of 1290 that is between 0 and 360. So now, whatever I do with that 1290, or whatever I was interested in regards to that 1290, should be the same information in regards to 210. So much easier. If you had a choice of coefficients, back to Algebra 1 or Algebra 2 or college algebra, if I gave you a coefficient for a quadratic that was 1290, and you could turn it into a coefficient of 210, wouldn't you much rather use the 210? Yeah, it's the same concept. Okay, that's why we have coterminal angles, or it's why we talk about them, is because it makes some of the algebra later on a little bit easier. I already talked about getting good at fractions, right? I think the second byproduct of trig, okay, and I see this every year, is that people get so much better at their algebra 1, algebra 2, their college algebra facts, as we work through trigonometry. Okay, it's just kind of the nature of the course and how we start to analyze things. It builds your algebra, I think, exponentially. All right. Now, before we get into talking about this, I want to talk about a little bit of an issue that some people have in regards to units with dealing with radians. Okay, and I put this description on my website, kind of show it to you here. It's under 5.1. But it's a question somebody asked, and it's a common question throughout pretty much any trig course that I've ever taught. As we start going through and applying some of our formulas, this next formula is going to deal with arc length. We'll see a formula dealing with eventually linear velocity, angular velocity. If you're in physics and you talk about those things before, you maybe have a jump start anywhere else. But these two formulas talk about this here is angular velocity, and this one down here is linear velocity. Those are just the formulas. If we look, I just want to look at the units, okay? Because when we talk about, let's say, linear velocity is simply how fast am I going in a straight line. It's distance divided by time, okay? If I take distance divided by time, I'm going to have a rate in regards to my units, right? I'm going to have like miles per hour. or feet per second, or something like that, okay? But if I look at how we go through and figure out linear velocity with these components, okay? So linear velocity is equal to this thing here, okay, which is your angular velocity, times in the radius of your circle, okay? So we'll talk about this probably tomorrow in more detail. But your units here are radians over seconds, and here are their meters. So if I were to multiply my units together, because that's what we're supposed to do, when we go through any formula or any manipulation of units, we multiply the coefficients or the constants together, but we should also be doing the exact same algebra with our units, right? Okay, we should be doing that dimensional analysis with our units. And when we do that here, we get radians times meters up top, right? And we should get seconds times 1 on the bottom. So I should have units of radians times radians times meters divided by seconds, okay? But whenever we express this in an answer as a speed or a velocity, we go meters per second. And the radians just vanish. Does that make sense? Okay? Now here's the reason why, and that's the question the person asks, where do the radians disappear to? Okay? So the radians were never really there. Okay? I'm going to talk about this in a moment. But it says, that is, they only exist when written down, so the meaning is clear. Okay? So the meaning is that, we're talking about essentially an angle. Okay? It says not in a dimensional analysis sense. So the purpose of having radians in here is not for the cancellation purposes that we go through when we multiply units together. Okay? That's what the conversions and reducing, stuff like that. It's all kind of wrapped up in the word dimensional analysis. Dimensional meaning, if I'm talking about just a length, that's a first dimension. Does that make sense? Talk about an area, that's a second dimension. There's a left or right, up and down, or a front and back, and left to right, something like that, right? There's two components to area. If I'm talking about volume, that's third dimensional, right? There's three components. There's left, right, up, down, and then forward and backwards, right? Depth, okay? So when we're talking about radians, okay, so recall that the definition of an angle in radians is the ratio between the length of the arc and the radius of the sector subtended by that angle. Okay? And when we did it, when we talked about the definition, we went all the way around the circle. So the arc was the entire circle, right? And the radius was just arc. But when we divide those out, okay, think about the radius. Radius is a length, right? Let's say it's feet. And the arc is also going to be a distance. Let's say it's feet. Okay? Well, when I compare those, if I go radius, which is in feet, maybe, and I compare that to the arc length, or maybe the entire circumference, that should be in feet as well, right? Well, dimensional analysis tells me those things cancel out, right? So, and when that happens, what we do is we introduce the radian, just to make sure that, it's just a constant that we have there, but we want to make sure we understand what that constant's representing. It's representing an angle, and that unit then is radians, okay? So radians is a unit, it just doesn't have a dimension, okay? So, when it says there, thus the dimension, i.e. the units, of an angle is length divided by length, you have nothing left over. They cancel each other out, which means it's dimensionless, okay? But we use the radian unit notation to remind ourselves, to make it clear that we're talking about an angle. Does that make sense to everybody? If it doesn't make sense, that's okay, I think. But what I want you to understand is that as you go through some work here, we're going to do some work here with some very simple formulas. And you're going to be left with radian times feet as a unit. But when I type that into WebAssign, or I write it down on my test paper or whatever, I want to just write it as feet. Okay? Whenever radians are left over in regards to a dimension, to a length, or an area or something like that, you let them disappear because they're essentially dimensionless. Is that okay? I don't like you guys obviously know this maybe about me, I don't like just give you something, tell you, hey, just do it this way because that's what we do, okay? Or that's just the practice that we go. I want you to know why, okay? And that's the reason why as we go through these, if we have radians left in our answer, predominantly we're going to cancel them out or let them disappear We just be left within the other units, okay? Usually distance. All right. So it says in a circle of radius r, the length s of an arc that subtends a central angle of theta radians is s equals r theta. All right. We did this in geometry. But we did it in geometry with this formula. We took, let's just say that I've got some circle here, and I'm going to talk about maybe that angle right there, and I call it theta. Okay. In geometry, that angle theta was some portion of 360 degrees, wasn't it? And if I want to find the arc length, when it says subtend or subtended, it's the arc that is between the rays of this angle, okay? Or it's the arc that is cut off by those rays of the angle. So the arc we're talking about here would be that green arc. Is that okay with everybody? Okay. So I want to find the arc length, the measurement. In geometry, we said it's whatever this angle was in degrees divided by 360. So that gives us basically the portion that arc or that angle is of the entire circle, right? And then we multiplied it by 2 pi r. What's the formula 2 pi r? Circumference. So we took theta divided by 360, which gave me the percentage or the portion that angle is of the entire circle, which ultimately then tells me that this green arc is that exact same portion of circumference, right? We multiply that out and give me arc length. The last finding, that works when we're in degrees, but in this class we like to deal with radians, right? Okay, and eventually in a physics class we like to deal with radians. So what is equivalent to 360 degrees in radians? 2 pi. So I put 2 pi right there. What happens to the 2 pi here and 2 pi there? Cancel out, right? And all you're left with is theta and r, right? That's the development of that formula. Okay? This is S, which is arc length. I don't know why we use S. But this represents arc length is equal to r, radius of your circle, times theta, which was the angle you're interested in, but in this case, theta has to be in radians. Okay? So, if theta has to be in radians, a lot of times what they do is they present you a problem that deals with degrees. Okay? Because they try to get you to realize the importance of being able to jump back and forth between radians and degrees. Okay? So, we want to find, I just draw a picture. You don't need to draw a picture, I don't think, every single time, but initially it's probably a good idea. Find the length of an arc of a circle with a radius 10 that subtends a central angle of 30 degrees. Okay, so we've got a central angle here. Theta is 30 degrees. And the arc that we would be subtending would be the arc that is in between those two rays, right? Or the arc that of the circle that is cut off by those two rays. Obviously, that circle should be going on forever, right? But we're only interested in the length of that thing right there. So the formula for this is S is equal to R theta. Well, S is the length that we're looking for. R, they say, is 10 meters, right? So S is equal to 10 meters. And like I said earlier, I like to, a lot of times with our formulas in trig, I like to put in the units. Those of you that are in physics, I think you find the same thing out when you put things into a formula because of all of the varying and differing components to a lot of your formulas in physics. You want to put your units in because your units are as important, if not more important, than your number, right? Okay. If my units are completely off, if I should be finding miles per hour, but I just found feet per second, does my number even matter? No. Okay. So I want to make sure that my units are correct as we're going through these things. So I like to put those in first, or not first, but inside the formula as well. And now, theta is that angle, right? And what is our angle measurement in right now? Degrees. But the formula says it should be radians, right? So we need to go to the side. We need to take our 30 degrees. And we need to do what we did with it last week and convert that into radians. If you remember, that's how we did that, right? So now what's 30 divided by 180? 1/6. So I get pi over 6 radians. So here, my theta is pi over 6 radians. My hopes are for you that eventually we just memorize 30 degrees. Once I see 30 degrees, you always associate it with pi over 6. Okay? So I get that. Now we'll multiply those together, right? And we get, what, 10 pi over 6, which if I reduce that, I get 5 pi over 3 meter times radians, right? Now, arc length should be a distance, right? And everything that we've talked about from second grade to now in regards to measuring something has never had a unit radian in it, right? It's always been meters or centimeters or feet or miles or whatever. So, just keep this in mind. These radians, okay, they were only here to remind us that that is an angle. So they are dimensionless. They don't need to be in there. So our answer is just 5 pi over 3 meters. Is that all right? You guys remember back in geometry, about halfway through the year, I started working with you and said, okay, let's try to keep our answers as exact answers. Let's not worry about decimals. Okay? This is the reason I wanted to build that skill with you guys, because everything that we do is going to be looking for that 5 pi over 3. They don't want that to be 5.2 meters. They want to leave it as 5 pi over 3. Okay? Does that make sense? Now if I go to Lowe's and I say, hey, I need some rope, and it needs to be 5 pi over 3 meters long, they're going to probably tell me go across the street to Menards. Okay? I'd go to Lowe's with 5.2 meters in mind, right? Okay? So there is always context of when to use exact values and when to use rounded values. For the most part in this class, if it's possible, we want to use exact values. Okay? The next question is a similar type thing. Okay? But now we've got the formula S is equal to R theta. And just like any other formula, if I have multiple components in my formula, we should be able to solve for any one of those components. S is the component that we usually solve for. That's the one that is kind of most asked for. So that's why the formula is S equals R theta. But just go like distance equals rate times time, right? That's a formula, but don't we sometimes want to know time? Well, sometimes we want to know rate. Okay? So same thing here. Arc length is equal to R times theta, but sometimes we want to know R is. Sometimes we want to know what theta is. So when I draw this picture, it says a central angle theta in a circle that has a 4 meter radius. So draw my circle here. Says that radius there is 4 meters, so R is 4. Says is subtended by an arc of 6 meters. So my arc might be that arc right there. And it's saying it's 6 meters. They want us to figure out if we have that situation going on, where arc length, remember, is S, right? If we have that information, can you work back inside? And can you find that angle theta? Well, we've got the components that build this formula, right? S equals R theta. S is 6 meters. R is 4 meters. Do we then have enough to solve for theta? Thank you. Just divide by 4 meters, right? So we get 6 meters divided by 4 meters is equal to theta. And that ends up being 3/2, right? What happened to these units? Canceled out, right? And when they canceled out, it creates now our result for an angle, correct? So just like before, when we had radians, radians were dimensionless because it was a foot divided by a foot, or a mile divided by a mile. Here, it's a meter divided by a meter, right? So previously, the radians disappeared, but now it's because we're interested in what the angle is. We reappear that radian to make it clear that theta is representing an angle, and we know that it's now in radians and not in degrees. Okay? Now, a lot of times, I'd probably say 90% of the time, you're going to deal with radians, and it's going to have a pi with it. Does that one have a pi with it? No. It's already inside it. Okay? The 1.5, if that gives 1.5 radians, the 3.14 number has already been multiplied through there. Okay? So let's see something here. If I have 1.5 radians, let's do this. I've got obviously pi is equal to 3.14 radians, right? Okay. So let's take pi and divide that by 2. I get that number there, correct? Well, pi over 2 is how many degrees? We're talking about on Thursday. Yeah, if that arc right there is pi, then that one is pi over 2. So this is 1.57. So if I look at that angle right there, theta, that's 1.57 radians, correct? Well, what we just found is 3 over 2 radians. Well, 3 over 2 is 1.5, isn't it? So wouldn't you agree that maybe that angle right there is 1.5 radians? Is that doable? Okay. And if you wanted to check this, could you take 3/2, see how many degrees this is, 3/2 radians times 180 degrees over pi radians? Now, if I multiply what's 3 times 180? 540. Okay. And then divide that by 2 times pi, right? Now, we should get something relatively close to 90 here. 85.94. Relatively close to 90, right? Okay. So when I see that 3/2, there should not be a pi on that. It's already inside the 1.5. Okay. And what I mean by it being inside the 1.5 is that it's some multiple of pi is already in there. It's not a whole pi, because obviously 1.5 is not a whole pi of 3.14. Is that doable? Make sense? Okay. That tends to be something that people struggle with later on as well. All right, we're in a couple minutes here, but we should be able to get through this form. This isn't too difficult. And the development of this is similar to the development of the arc length formula. If you remember back to geometry, if I wanted to find the area of a sector, okay, so if I've got my circle here, for instance, maybe we're interested in that blue region. We call that a sector, right? Okay, it's a section of a circle. It's a piece of pie or a piece of pizza or whatever. Back in geometry, we said that this thing was equal to whatever theta was, and theta is going to be that angle, so your central angle, divided by 360 times pi r squared, right? Pi r squared then is your area formula for a circle, okay? But now, in trig, we don't want to do this with degrees, we want to do it with radians. So what does this 360 turn into? 2 pi. So now I get pi r squared there. What happens with the pi's? Cancel. So I'm left with, theta r squared up top, okay? And I'm left with 2 in the bottom, right? Well, is that formula there the same thing as that formula there? Okay. But this is a reason why we like to use radians instead of degrees, because that That's just more natural. We get a lot of cancellation to occur in that concept. Okay? It makes our calculations a little bit simpler. So it says find the area of a sector with a central angle of 60 degrees. Well, this is where using this formula might be problematic, is because everything's in radians, but the information they provide me is in degrees, and they do that on purpose. Okay? So what we want to do, take our formula, area 1/2 r squared theta. We've got 1/2. R, radius is 3, right? So, and it's 3 meters. So I'll square that. And now theta says 60 degrees. Does anybody know off the top of their head the equivalency for 60 degrees in radians? Pi over 3. And if you can't do that right away, all you got to do is come to the side and go 60 degrees times pi over 180. That's pi radians. Okay, 60 and 180 cancel out, right? I have a factor of 60 in both of them, 3 times in the 180, and I get pi over 3 radians. That's my units. Okay, now if I go 3 meters squared, what's 3 meters squared? What's that give me? 9 meters squared, right? Okay, so now I've got 1/2, 9 meters squared, times pi over 3 radians, right? That 9 and that 3 cancel out, leaving me 3. So now my numerators, I would have, what, 3 pi? 1 times 3 times pi. I'm going to have meters squared times radians. And on the bottom, I'll have 2, right? Now, meters squared times radians. Now, think about this. We're looking for the area of something, right? The area has always been feet squared, inches squared, centimeters squared, miles squared, meters squared. Never had radians attached to it, right? So that radians is a dimensionless unit, so it's not essential to our answer. And we just get rid of it. 3 pi over 2 meters squared would be the area of that sector. Is that all right? Okay. That should get you somewhere. You could probably finish 5.1, and I'll extend the due date probably through Wednesday. But you should probably be able to go through the web assignment and get 5.1 done. These formulas give you maybe a little jump start on 5.2 tomorrow, or sorry, 5.1 day 2. Tomorrow we will go through and discuss linear velocity and angular velocity, do a series of questions with those, and hopefully develop maybe some relationships between the two, and that should help you finish everything out of 5.1. All right. Those of you that have missed